Okay, AP students, we're going to do another warm-up problem this morning that has to do with work and friction. So let's start with a ramp. And so I just realized if I hold this here for a second, it makes a nice straight line. Not that it's really that important, but hey, I'm just playing with my new toy. So let's have a box here at the top. And let's say that we are interested in knowing the velocity of the box when it reaches the bottom. Lily, what's your favorite number? She says 53. Okay, so that'll be 53 degrees. Let's go. Ryan, what's your favorite height of a ramp? Ryan likes 7 meters. I'm not sure why, but that's what Ryan likes. Okay. And let's throw this one out to Maggie. Maggie, what's your favorite mass of a crate? Maggie likes 15. I'm not sure why. That would be my last choice, but she's kind of different. So Maggie likes 15. Okay. So before we get started on this, remember that there are really 2 ways you could have solved this one. And I'm not going to solve it the first way, but I would show how it would work. The first way you could do it is to solve it using force and then motion. You would have to figure out all the forces going up and down the ramp, right? So you'd have to deal with these forces right here. You'd have a frictional force up there. And which reminds me, the frictional force, I forgot to ask Garrett what his favorite frictional force is. And he likes mu of 0.37. Okay, thank you. All right, anyways, back to forces of motion. You could figure out all these forces here, and you would say F net equals ma, and then you would say, well, there's the parallel force that's being opposed by the force of friction, and all that's equal to ma, and then you would go mg sine theta here, you would go mu times the normal force here, which is mg cos theta, and then you could figure out your a that way, and then you would figure out the a, you'd have to go like a vf squared formula, and because you know the d, and you would get vf squared that way. Okay. That's the long way to do it. Now that we know energy, it's just going to be an easier way. So the better way, or I should say that often the easier way is to use energy. Always ask yourself, what kind of energy do you have at the beginning? What kind of energy do you have at the end? And do you lose or gain any along the way due to work? So we start with potential energy at the beginning. We're going to lose some of this energy due to the work done by friction as it slides down this ramp. And what's left over is going to be the kinetic energy at the end. I want to point out a little small idea here is that work is, of course, a transfer of energy, so it is in the units of energy, so work is in joules. A common mistake is for students to do this. Energy minus the force due to friction equals kinetic. But now you gotta have a dimensional problem, because now you're trying to take joules minus newtons, and you just can't do that. So just a heads up, that is a common error, common mistake. You need to work. Okay, so back to what we were doing. The total potential energy at the top is going to be mgh. The work done by friction is going to be the force of friction times the distance d, which is the length of this ramp, which obviously we don't have, but we have enough information we could get it. And then that is going to be equal to the kinetic energy at the very, very end. Okay. So let's start with the thing we don't know yet, which is this term right there, this force of friction. So let's dig in a little deeper. mgh minus, okay, force of friction is always mu times the normal force. D equals 1/2 mv squared. And again, I'm showing every single step in this case. The normal force on a ramp is mg cos theta. That is, again, this force right there. So this would be mgh minus mu sub k mg cos theta d. We can't forget the d. And I want to point out, without the d, this is the force of friction. So the d is what makes it work. 1/2 mv squared. Alrighty. And we've basically boiled it down as far as we can get it, and now it's solving time. We're trying to solve for v. What is the final velocity as it exits this ramp? So I'm going to jump down to here a little bit. Notice that the mass is irrelevant to the physics of this question. Again, it's very interesting in physics how often the mass of objects is irrelevant to the physics that happens to them. So GH minus mu sub k g cos theta d equals v squared all over 2. That's the 1/2 v squared. Now we can multiply both sides by 2 and take the square root. So the final velocity is going to be the square root of 2g. I'm just factoring a g out. I just like to factor things out if I can. H minus mu sub k cos theta d. Still cannot forget your d. All right, and now it is calculator time. So VF is equal to the square root of 2 times 9.8 times 7 minus 0.37 cos 53 times d. Well, I guess technically I didn't get d yet, but since we're given the opposite sign, that would be a sine function. So sine 53 is equal to 7 over d. So d is equal to sine 53 divided by 7. So there'll be sine 53 all over 7. So that's our d. And I don't know what this final answer is, but I bet you do. So let's just give it a variable. Let's call it smiley face. So the final velocity as this box leaves a ramp is smiley face. So that is today's warm-up on the using energy and the work due to friction to solve for final velocity.